Hi, my name is Steve Grice with PageKey Solutions. Today I'm going to show you how to create a binary search tree in Python. So first we'll go through the presentation and talk about all the theory behind binary search trees. Then you can dive into the blog article that accompanies this video, which will be linked in the description. We'll start out with an example tree and we'll talk about some basics about binary search trees. If you look at this tree, you'll notice that it's sorted in a way, and it does qualify as a binary search tree. Our root node is the first one that was inserted into this binary search tree. A binary search tree is very much binary. It's 0 or 1, left or right. So the data that you store in the tree has to be sortable. It doesn't have to be numbers, but it certainly lends itself to that. So for this example, we have 50 as our first node stored. The major takeaway is that anything to the left of a node is less than that node's value. Anything to the right of a node is greater than that node's value. Key methods in a binary search tree include insertion, search, and removal. So we will go through each of those methods, how to insert, how to find, and how to remove something in a binary search tree. For insertion, we're going to insert a node containing the value 63 into the search tree that we saw a few slides ago. So as you can see up here, I created a little node to hold 63. So we're going to go through the insertion process step by step. The first thing to consider is the root node. Is 63 greater than, equal to, or less than the root node? Well, it's greater than, so we're going to go to the right. Now we're going to ask the same questions about a node containing 75. Greater than, equal to, or less than? Well, 63 is less than 75, so we're going to proceed to the left. Now we're looking at a 60 node. 63 happens to be greater than 60, so we're going to proceed to the right. Now it may not show it, but 60 here, although it is a leaf node, has a little holder for left node and right node. So when we go to the right, we see that it's empty, and we create that new node for 63 and insert it. You would follow the same process for inserting any node, with the exception that one is equal. For example, if you wanted to insert 50 into the tree, you would get to this first node and realize that 50 is already in the tree, and return a value to indicate that. Now we'll go over search, how to find something in a tree. It's basically the same as inserting in that you traverse left or right based on greater than, equal to, or less than. We're searching for the node that is equal to. So, to find a node equal to 42, we start at 50. Well, we're searching for 42, which is less than 50, so we'll proceed to the left to find that node. Now we're looking at 25 versus 42. Well, it's not equal, so it's not what we're looking for. 25 is less than 42, so we'll proceed to the right. Now we've found what we're looking for. 42 is equal to what we're searching for. We've found it and we can return true. In any other case, we'll traverse the tree step by step. Say if this was 43, we would continue to the left and find nothing there. Once we reach the bottom, or where there's nothing left, we know that we can't find it anywhere in the tree. We can make this assumption fairly because the tree follows a very specific format. The node on the left of a given node in the tree is always less than that node. The node to the right is always greater than that node. Removal is a tough case for binary search trees, and we're going to talk about this quite a bit. Here's an example of a very easy case where we have a leaf node that we're trying to remove. We want to remove 42 from the tree. Once we find that node, all we have to do is set the parent's right branch to nothing. So basically, that's all we do. We just set the right node of this 25 to none. A higher level language like Python will take care of removing the object for you and garbage collection and all that good stuff. C or C++, you'll definitely have to clean up your references, but it's the same idea behind it. Like I said, deleting things in a binary search tree is not easy. The best way to go about it is to break it into a number of discrete cases. The way I've laid it out here, it's in 7 cases. The first case is that the tree is empty. When this happens, you're trying to delete something from an empty tree. Obviously, you're not going to be able to find it, so you just return false to indicate that you didn't find it and you didn't delete anything. Same thing for case 2. If you can't find the node in the tree, you can't delete it from the tree. Just indicate this with your return value, if necessary, and continue. Case 3 encompasses all special cases for deleting a root node in a tree. I won't cover this in the video because it's very similar to deleting any other node, with a few exceptions. For the full code, check out the blog post. So if a node has no children, that's definitely the simplest case. The first step of any deletion is to find the node. So we iterate down, same as the find method, and we find our node with value of 1, which we were looking to delete. No left node, no right node. All we have to do is go to the parent and say, hey, your left child is now none. A nice language like Python will take care of everything for us as far as garbage collection and cleaning up your references. However, if you're using C or C++, definitely make sure you avoid memory leaks and clean up your references. For case 5, if a node only has a left child, you're going to first find the node. Here it is, node with value of 3. We want to delete it. However, if we just remove, like we did before, the left child of this tree, we lose that entire subtree. So, what we really need to do is move up this left child. In other words, set the value to 1 and then that left child to none. So basically just move up that left child. So now it's like that value of 3 never existed, and we just have that value of 1 there, effectively deleting it. Decrement the count of nodes in the tree if you have to, and return true. Yes, we deleted something, and you're good to go. It will be a similar case for number 6, right child only. You're just going to basically overwrite the existing value by moving that child up, and you're done. Decrement the count and continue. A more difficult case is when you have both a left and a right child. I actually had to stop and add a few extra nodes to make this make more sense. So there are 2 ways of going about this that will work in any case. You can go down the left tree, or you can go down the right tree. In this case, I added nodes on the right tree, so we'll go with that. So one way of doing it, if we were to delete a node with value of 75 out of this tree, we go to the right by 1, so we take the right child, and then we go all the way to the left. So we go in the opposite direction as far as we can. There could be any number of other nodes in this tree. I just added these few for clarity. So we go to the right one and go all the way to the left, all the way down until there's nothing to the left. That takes us to this 118. Then we're just going to drag that 118 all the way up into our existing node. So our 75 is pretty much deleted. Now what happened and why did we do that? Well, if you look, our tree still follows everything that a binary search tree should. You go to the left, it's smaller. You go to the right, it's larger. If we had done anything else, this wouldn't be considered a binary search tree anymore. The order would not be, the order of each node would have been thrown off. Going right one and all the way to the left grabs a leaf node. Overall, it's the simplest way to make a shift of one node and delete the one that we're going for. I said earlier that there are 2 ways of doing this. Actually, the second way just involves going to the left and then all the way to the right. If we change our nodes around a little bit, you'll see that it works the same way. We want to delete 75, so we go to the left and then all the way to the right until we can't find anything else to the right. And we move it up. Now our tree is still in order, and the node that we were trying to delete doesn't exist anymore. Perfect. One more important concept with binary search trees, or really with any tree, is how can we traverse the tree? There will be 3 ways of doing this that we'll go over today, which is pre-order, in-order, and post-order. And each of them has their own applications. All 3 traversals are similar in that they perform the same steps, just in a different order. So the pre-order traversal will first execute the node that it is on and add it to the list. Then it will go to the left, and then it will go to the right. Basically, we just need our recipe up here in the upper right, and we're going to apply it to each node. Like each node has its own brain. It's going to think to itself and perform these steps. So if we're going through the traversal, this node is thinking, okay, I'm going to add myself. Now my left tree can do whatever it wants. It talks to its guy, its left-hand man, and says, go for it, do your thing. He's following the same instructions, so he adds himself, 2. So this is 1, this is 2. Then he says, okay, left-hand man, go do your thing. And then this guy becomes 3rd. Then that completes, and we go back to this guy, and he thinks, oh, my 3rd step is to tell my right-hand man to do his thing. So then we go down here, this guy becomes 4th. Then it returns to him, and he's like, I'm done. Returns to this guy, and he says, well, I still have 1 step left. Let's go to the right, and the same process repeats over here. For in-order traversal, which, let me just note that this is a very useful way of sorting your data. If you have data in a binary search tree and you need it in numerical order or sorted order, perform an in-orders traversal on the tree, and that will provide it. So we'll go through and just ask each node the same questions. Well, we're doing in order, so this guy says, first I need to tell my left-hand man to do his thing. This guy says the same thing. left goes first. Once we get down here, he says, I have no left-hand guy. Let me add myself. Now I have no right-hand guy, so I'll go back up. But he did add himself. He's position 1. This guy says, okay, now it's time to add myself. That's step 2. So he becomes number 2. Then he says step 3 for in-order traversal is definitely to let my right-hand man do his thing. Same idea, this becomes 3rd, and we go back up and up again since we're finished. And back here, he adds himself. He's in position 4 now. And now, right-hand man, do your thing. And this entire side of the tree is going to follow the same steps. Post order, if you haven't caught on already, follows the same pattern in a different order. So, this guy, he is selfless. He wants everyone else to go first. He says, left, do your thing. And this guy says the same thing, left, please do your thing. And left has nobody to report to. He just says, okay, I'm number 1. He goes back. This guy again says, right, please do your thing. Number 2 goes, and it follows the same idea. So that's post-order traversal. Thank you for joining me for this presentation on binary search trees. I hope you learned something. I hope it helps you out. The entire implementation of everything we talked about today is available in Python, along with snippets and additional explanations on PageKeySolutions.com/blog. Make sure to like, comment, subscribe, and definitely sign up on PageKeySolutions.com/blog to be notified of any new posts. Again, my name is Steve with PageKey Solutions, and I just want to thank you for watching this video.